All right, so today we're going to talk about exponential and logarithmic models. And basically, we're talking about applications of logarithmic equations and exponential equations. And typically, when we talk about applications, we're talking about some wordier problems. So we've gone ahead and made a notes sheet for you to save you some time of writing problems down. Okay? Please do not work ahead. Please stay with me, all right, so that you can hear everything that I say about a particular problem. All right? So first, we're going to talk about our compound interest. Okay? Now that we can solve exponential equations, we can take our compound interest problems and answer something about the time, which is kind of what we previewed in our homework last night. Okay, so let's go ahead and read through this. How long will it take an investment of $1,000 to double if your interest rate is 8% and interest is compounded? We're going to answer this quarterly and continuously. So first of all, let's pick out some information. $1,000, what is that? Okay, is it like the amount or is it the principal? Okay, it's the principal. And if we want our principal to double, that means we're looking for our amount to be what? $2,000. Okay? 8% is our interest rate. So remember, I need you to change that to a decimal. Okay? And in the first part, if we're talking about compounding quarterly, then that means N equals 4. Okay. So, if we have our equation of A equals P times 1 plus R over N raised to the NT, and we have all of this information, we can go ahead and plug in $2,000 for A, $1,000 for P. Our rate is 8%. Quarterly, and we're solving for time. We want to know how long this is going to take. So we are solving for time. Okay? All right, so what's one thing we can do? We can divide by 1,000. And what happens, when we take 2,000 divided by 1,000, we get, okay, that should not be a surprise. We want this to double. We don't even need to know how much we have originally. If it's going to double, we're going to get 2 when we take the amount divided by the principal. Okay? 1 plus 0.08 over 4. We can actually calculate that and write it down because it's not a crazy long decimal. What is it? 1.02. Thank you. Okay? So now we have a nice, simple exponential equation where our exponential piece is all by itself. Okay? So when that happens, we can take and switch forms. So we have log base 1.02 of 2 equals 4t. What?
It sounds like the number 4.
Oh, 4t. Yes. You have to make 4t. Okay, so what I need you to do is I need you to take the change of base formula for this guy. And then since it equals 4t, we can divide that 4 over. Eli, what'd you get?
8.751.
8.751. Do you agree with Eli's 8.751? If you don't agree, can I help you with your calculator? Do you think I want you to just write 8.751? What do I want you to write next to it? Years. Time is always in years with compound interest. Okay, think about it. When we go to compounding continuously, is it going to take more or less time? Okay, it's going to take less time. Okay, the more you compound, the more money you're going to make. Okay, so if we're investing, it is not going to take us long for us. So let's go ahead and write the equation for compound interest. That's an easy one to remember. We like to call it PERT, right? Is PERT Plus still around? Is that still a shampoo? I'm guessing by your looks, no. So growing up, PERT Plus was a very popular shampoo. There's lots of commercials about it. Anyway, so our amount is $2,000. Our principal was $1,000, and our rate was it 8%? Right? Okay, so now this is the equation that we need to solve. Very similarly, we need to divide that 1,000 over, and again, I'm going to reiterate, since we're doubling, when we divide, we get a 2. That's not a surprise. If we're tripling, we get a 3. If it's being cut in half, we get 1/2. All right? Hopefully your investment isn't being cut in half, but in a different situation, right? Okay, so now we have our exponential piece by itself, so we can change forms. Log base e of 2 equals 0.08 t. So log base e of 2 equals 0.08 t. Okay. So in your calculator, we can determine what the natural log of 2 equals. And then to solve for t, we can take that coefficient and divide it over. So we have a natural log. All right, what do we get? I bet 8 point something. Okay, so like we said, it won't take quite as long. I mean, we got, what, like a month ahead. So it's really not that much faster, but it's at least a little bit faster. Okay, so you can expect some of these problems in your homework tonight. Okay, we're dealing with our compound interest, but now we're solving for t in the exponent instead of the amount on the other side. Okay, let's look at the 3 different types of models down below. 2 of them we really already talked about. The third one looks kind of strange. Okay, so the first 2 are modeling exponential growth versus exponential decay. All right, I want to kind of talk about what is going on right here. What could you compare this to? What equation that really we've talked about already today does this sort of look like? Kind of looks like PERT, right? And let's think about what everything means with PERT, okay? Y is always going to be our amount, okay? A, that coefficient, all right? What is the P in our PERT equation? And what does that mean? Okay, how much do we start with, right? So if we have an exponential growth or decay model, that coefficient right there is still going to stand for our initial amount. Okay? And then whatever that B is up there, that's going to be your rate. If it's positive, you're going to have exponential growth. If it's negative, and I'll come back, you're going to have exponential decay. All right? If it's positive, we're growing. If your exponent is negative, we're decaying. Okay? There's really no better way to say it. All right? So that's something to keep your eye out for. If you know that, like if you have bacteria that is growing, or if you have a population that is growing, we need to make sure that that exponent is going to be positive. However, if you have some sort of population that's decreasing in value and you're modeling it exponentially, you better have a negative rate if we're losing members of a population. Okay? We have graphed these, all right? But what we're going to do today is we're going to use their models to represent either a growth or decay of some sort of tangible item, whether it be flies or bacteria or a population of people, okay? And then find some information about it. Okay. Now our third model, this is what we call logistic growth. It looks kind of crazy, right? So this is what we use to model sometimes the spread of rumors. Okay, is a very popular example. Maybe we're talking about some sort of illness in a certain population. So if we talked about the spread of a rumor here at school, there is only a certain number of people that can hear it. It's 1,900. So what happens when we spread a rumor is it starts to spread really quickly, but then the more people that hear it, the slower it spreads until it kind of just tops off at what we call a carrying capacity. Okay, no more than 1,900 people can hear that rumor in this building, so it's going to start to level off. Okay. If we think about, I think we're going to go through an example of some sort of illness on a college campus. There's only so many people on a college campus. That disease is going to spread really quick as more people interact with each other. But then you start like overlapping people. Like if two people have already been exposed and they're sitting next to each other, well, they're not going to spread it to each other. So it grows really fast and then it kind of tapers off the more people get it. Okay, so this is called logistic growth. When you get into, like we did a lot of stuff with this in my Calculus 2 class, okay? But the information will all be given to you, so I'm not, A and B are still there. A is what we call the carrying capacity, but everything's going to just be given to you in that sort of model, okay? So we have two questions that we need to get through. They're both on the back side, okay? And we'll try to spend about, 10 minutes with each one. Okay? This one's probably going to take a little longer than the next one. Okay? Okay, so go ahead and just read through the problem. Okay, so if any of you are interested in a major in biology, there's a pretty good chance that you're going to be working with fruit flies at some point in your college career. That is a very popular research project that people do, is the growth of fruit flies. They're really tiny and they're really kind of gross, but their lifespan isn't very long. Okay. Has anybody ever gotten fruit flies in their house on accident because they like left either like a pumpkin or like your bananas get moldy or something like? They're terrible. Okay. Throw away your fruit before it rots. Okay. So we have. That's not what I wanted to underline. I wanted to underline exponential growth. Okay, it is telling us that this fly population is growing in an exponential growth pattern. So we know we have y equals a e to the bx. Okay, and if you use t instead of x, I have no problem. Okay. Actually, do you mind if I do that? Can we erase and use t since we're talking about time? Is that okay? We have the liberty to do that, right? And it doesn't matter what variable you use, okay? But since we're talking about time, I'm going to use t. Okay, so we know that after 2 days, there are 100 flies, and after 4 days, there are 300 flies. Do we know how many flies we started with? We do not. We do not know A. Do we know the rate at which they are increasing? No, so we do not know B. So we need to use these two pieces of information to solve for A and solve for B. So this is what we know. After 2 days, I'm going to underline it in red. After 2 days, there are 100 flies. So we know that the amount is 100 after 2 days. Okay. And we know after 4 days there are 300 flies. So the amount is 300 after 4 days. Now we have to solve for A and B. We have two equations. What are our options? We have two equations and two unknowns. We have this strategy called substitution, right? Where we can like solve for something and plug it into the other one, okay? Which maybe is going to be easier to solve for, A or B? I would say A. So we can come over here and we can say that A equals 100 divided by e to the 2b. All I did was divide that e to the power over. And what we can do is we can come over here to the green equation and we can say, well, A is the same thing as 100 over e to the 2b. Okay. Well, is everyone okay with I solve for A and I put it in for the other one? Okay. Well, now we need to work with it. Now my A is gone and we can solve for B. So over here on the right side of our equation, we have 100 e to the 4b divided by e to the 2b. When we have exponents and we're dividing, we can subtract our exponents. So e to the 4b divided by e to the 2b, we can subtract that to be 4b minus 2b is 2b. Do I need to go through why that is again? Well, I have an A in this equation and an A in this equation. They're the same A.
Oh.
So I can solve for A here and replace it over here.
So if you're subtracting the 2 and the 4, wouldn't you also subtract the b?
Well, it's 4b minus 2b. So combining like terms, there would be 2b.
Sorry.
Nope, that's okay. All right, so now let's solve for b. We can go ahead and take this 100 and divide it over. So we have 3 equals e to the 2b. Okay. So now we're going to have to change form. So we have base e. So we have log base e of 3 equals 2b. Okay. Now, we are solving for the rate in which this population is growing. And since it's growing, you better get a positive rate. Please type in the natural log of 3, close your parentheses, and divide it by 2. Okay. Now, I told you that I don't like you to round and use a rounded answer in your work. Okay? So if we're going to eventually round to 3 decimal places, let's go ahead and round our rate to 6 decimal places to help us with accuracy. Okay? 6 decimal places, what would that be? Point. 54 what?
9306.
Okay? That's the rate in which our population is growing.
Oh.
That's very quick, isn't it? Fruit flies grow quick. Okay? Now we can come over here and we can figure out what our A value is. So we have 100 over e to the 2b. And you can even use the b that's in your calculator. Okay, if you press second answer, that brings up the answer from before. You can also arrow up if you have a TI-84. You can arrow up and select the answer. Let's see if, last time I couldn't get my calculator to work. Let's see if it'll work this time. You feeling it? Come on. Okay, so we typed in the natural log of 3 divided by 2 to find our rate, correct? So, oh, look at that. The natural log of 3 and then divided by 2. And then to calculate A, we said, was it 100? Divided by, what was it, e to the 2b, right? E to the 2. Instead of typing out b, I can press second. Oops. Dang it. 100 divided by e to the 2. Second answer, right there, will just bring up what you typed in before. So instead of having to type it all out again, I just said second answer. Or you can go up and you can arrow up and you can highlight over it and press enter and it'll bring it up. Okay. So we have 33.33, right? What's 33.33? That's 33 in the third, right? Okay. How can I express it as a mixed number or a improper fraction? 34 over 3? 100 over 3? Okay. So our model would be y equals 100 over 3e to the 0.549306 t. Now, not all the time you're going to get a really nice number that can actually be a fraction. So if you have to round, you have to round. Okay? Yes.
Sorry, but when the e to the 4b disappears, is that because of
That's because we were dividing. Okay? So e to the 4b divided by e to the 2b means we subtract our exponents. 4b minus 2b is 2b. Mm-hmm. Okay, so this is our model. And so if it asks how many flies are there after 5 days, then we need to come down to our model and we need to plug in 5 for T. How many sides do you have?
Rounded up about 518.
518.8? Okay. Yes. That's what I got too, Kaden. Let me see what you typed.
I rounded.
Oh, yes. Okay, so Caden rounded to 3 decimal places on his rate, which affected his answer by an entire fly. Okay, that's what I'm saying. When you round your rate, go to 6 decimal places so that when you use it again and again and again, it'll give you a more accurate answer. Okay, now, what was kind of a pain about this problem is they did not give us the initial amount. But if they tell you we begin with 100 flies, then you already know your A value. Since they didn't give that to us, we had to solve for not only the rate, but also the initial amount, and that's what made it a little bit crazier than maybe a different problem. Okay? All right, we have about 5 minutes left to talk about our logistic growth problem. Okay? On college campus of 5,000 students, one student returns from vacation with a contagious and long-lasting flu virus. The spread of the flu virus is modeled by this. It's a logistic growth equation, okay, where Y is the total of number of students affected after T days. The college will cancel classes when 40% or more of the students are infected. So if I'm asking you to find how many students are infected after 5 days, you're plugging 5 in for where? T. That one's kind of nice, right? Anytime you have days, months, years, whatever, we know we're going to be plugging it in for time. So we have Y equals 5,000 over 1 plus 4,999E to the negative 0.8 times T. Okay? If you're going to punch this into your calculator, since you have more than one term in your denominator, you are going to need parentheses in your denominator. How many students are infected after 5 days?
54.0.
You agree? Oh my gosh, after 5 days we have 54 students. From the one person came back with this flu, and 5 days later 54 students are infected. Okay. So then part 2, how many days until the college will cancel class? Okay, so they're going to cancel class of 40% or more. I need to know, what is 40% of 5,000? Is 2,000? If you take 0.4 times 5,000, that's 40% of 5,000. That's 2,000 students. Okay, so the equation that we would have to set up, that's the amount of students we want. I mean, we don't want them to be sick, but in our equation, that's where we want the 2,000. Okay. And now our job is to solve the T. Okay, So I would suggest first multiplying that denominator over. And then I would take that through. Somebody help me out with that multiplication. The 2,000 times 4,991.
Oh, okay.
9993.
Okay, and once we get to this point, this looks more like something that I would have given you yesterday, right? Where we need to isolate e to the power so that we can change form. Okay? I'll tell you that it's 10 days. That's not very long, right? Cemetery. Okay. Your homework tonight, you do have a population question that has multiple parts. Okay? If it gets to the point where you're running out of time, don't skip the entire thing. At least do a few of the countries. Okay? At least do a few of the countries in the population problem if you're short on time. Okay? Oh, okay.
Do you think I could try to send that to Sarah?
Yeah, me too.